Yay!
Yay! Hey everyone, here is a classic problem that you will find in just about every textbook, and everyone who teaches it does this kind of problem. And this is finding a point where the electric fields from a couple of charges cancel. So can we find somewhere, let's say we have a positive charge and a negative charge and they're not the same charge. Where can I go? Is there a point where the electric field is zero? Due to these two charges. So that's what we're going to try to find out. But let's think about it for just a little bit beforehand. In fact, let's look at these three regions. Let's say region A, B, and C. All right, A is to the left of the plus charge, and B is in the middle, and so on. C is to the right. Okay, let's see if it is even possible, if the electric field could be zero in those regions. So let's look at region A. Is it even possible? Okay, so in region A, I've got the electric field from the positive charge is going that way, and the electric field from the negative charge is going that way. So could they cancel in principle? Yeah, they could. So this is certainly possible. Also, well, let's leave it at that. Okay, we'll come back and modify that maybe just a little bit. Yes, it's possible because the electric fields are pointed in opposite ways. Okay, in region B, is it even possible in region B? Okay, well, in region B, from the positive charge, it's going away. And from the negative charge, the field is also going to the right. It's going towards the negative charge. So notice that in region B, nope. It's not possible for the electric field to be zero because the electric field is going the same direction, right? There's no way those two vectors are going to add to zero in the middle. What about region C? Okay, now we have to be careful. In region C, look what's going to happen. I have a negative electric field, or I got the field from the negative charge is going towards the negative charge, right? Back to the left. And the field from the positive charge is still going this way to the right. So you might think, sure, in principle, it's like region A, right? It could be zero. But look, no matter where we are in region C, we're always closer to the stronger charge, right? So, and remember, the electric field dies off as the square of the distance. So nowhere in C are we going to be at any position where the 2.5 charge is going to overwhelm the minus 3.5 charge, right? The field due to the negative charge is always going to be stronger than the field due to the positive charge because we're closer to it. So C is nope. But you have to think about it carefully because at first you might think it is possible because the fields are oppositely directed. But the negative one is always going to be greater than the positive one. So nope, can't do it on that side. So we're just going to be talking about region A. Apparently it's possible, maybe, in region A for us to find where the electric field is zero. So here's what we're going to try to do. Here's what we want. The electric field due to the positive charge plus the electric field due to the negative charge is going to be zero, right? And they're going to be oppositely directed. So what we're really saying, this will make things a little bit easier. What we're really saying is we want the magnitudes to be equal of those fields. We already know that one's going one way and one's going the other way, but I want the magnitudes to be equal because then if the magnitudes are equal and they're oppositely directed, their sum is going to be zero. So this is what I'm after. Okay, so what is the magnitude of an electric field? It's just kq over the distance squared. Right? We don't have to, since we're just after magnitude, we don't have to worry about doing kq over r cubed times r vector, all of that stuff, which is what we need to do if we're trying to find the vector, the electric field vector. But the magnitude is just easy. It's just a number. It's just kq over r squared. Okay, so that means that I can do this. If I'm in region A, let's call, maybe I'm right here. Maybe the point is going to be right there. So let's call this distance r. The distance to the positive charge is r. So this is going to be, what I'm saying is I want k, q plus the positive one divided by the distance from the positive has got to be equal to kq minus over r minus squared, right, to that point. That's what I'm really after. Actually, when I do this, look, the k goes away, so I don't have to worry about that. Okay, so what this means is I can do this. R, the distance from that point to the negative charge squared over the distance to the positive charge squared is equal to, let's see, what's that going to be? Q minus just the ratio of the q's. Now you might think we're in trouble because I know what, I mean, R, the distance to the plus charge, I can just call that R. That's what I've called R. What's R minus? Well, I know what that is. I can write that in terms of R, right? This is R plus 0.6. That's still going to be squared over R squared is equal to Q minus over Q plus. Okay, so now I can put in what the magnitudes of these charges are. Let's see, what's that going to be? 3.5 over 2.5. This is microcoulombs, right? 10 to the minus 6, but it doesn't matter because that's going to cancel. We just want the ratio, the two. Okay. Okay, now, look, when I first solved this problem, I did the exact same thing that I see a whole bunch of students do when they first try to solve this problem, because you know, okay, let's go back to our algebra. We want R. We're trying to solve for R. We want that distance R. So what do? Well, I got R in a plus b squared term up top. So what you want to do, you think, is we'll start R squared plus, okay, I'm going to FOIL that out, right? R squared plus 1.2 R plus 0.36, right? And then on the bottom, I'm going to have R squared. And then I got this awful quadratic looking thing. This is going to be over R squared. Oh, no. That looks awful. You could do it. You'll get the right answer if you go through and solve the thing. But let's think about it. Because that's what I did. The first time I saw these problems, that's what I did. And it was a big headache. But watch, you can save yourself a whole bunch of work just by doing and maybe you've already seen this trick. You've already recognized that you could do this. Why not just take the square root of both sides? The left side is a perfect square. So the left side, just make it R plus 0.6 over R. Right? Just take the square root of the left side, and the square root of the right side is the square root of 3.5 over 2.5. That's going to be really, really easy, because then that gives you R plus 0.6 is equal to, what the heck was it, 1.18 times R. We're just about done, right? No quadratic. It saved a ton of work. So this means that 0.18 R is equal to 0.6. So R, if you do that, what did I get when I did this out? 3.3, about 3.3 meters. So this drawing is not really to scale, right? This point is actually way over there somewhere. But anyway, this is how far away, towards the left, this is how far away that point has to be. And then at that point, the electric field is 0. So that's the general prescription of how to solve these types of problems. And the trick is that if you don't see it first, you're going to want to know this trick, because otherwise you're going to spend a whole bunch of tedious time doing quadratics and so on, is once you reach this point, just take the square root of both sides, and that'll save you a ton of work. Okay, so on we go.